we're now going to extend the result of the previous video where we did separation of variables to simplify the classical wave equation, which again is written up here, by writing its solutions as a product of one variable functions in x and t. And where that leads us is from this linear partial differential equation to two ordinary differential equations, one in the coordinate x and one in the coordinate t. All right, we didn't really talk about the t coordinate in the last video. We mostly talked about x. But we also, at that time, showed the solution for a alpha greater than 0. And what I want to do now is look at what happens when alpha is less than 0. So that means now alpha would have to be equal to some parameter k minus k squared. So one of the things I want to point out is if I take the square root of alpha, this is going to be the square root of minus k squared, which is going to be k times the square root of minus 1, or the imaginary number I times k. So now we can take the solution that we had before for x of x. Remember, we wrote that solution as follows. We wrote x of x could be written as c1 e to the, it was kx, but I'll write this as square root of alpha x plus c2 e to the minus square root of alpha times x. And now with this new definition of alpha, we can write this as c1 e to the ikx plus c2 e to the minus ikx. Now at this point, if you are not familiar with complex analysis, you may want to do a little bit of review on the side to learn about this. But these complex exponentials actually have a very simple interpretation. And this is an interpretation due to Euler. So I want to write that down. If I have an exponential of e to the I theta, this is simply equal to cosine of theta plus I sine of theta. And it turns out it's not very difficult to show this. There's a lot of different ways you can do it. But this is an extremely powerful statement. And I'll note that one special form of this is that if we took e to the I pi, that would be cosine of pi, which is -1, plus I sine of pi, which is 0. So in other words, we get this very interesting equation here. E to the I pi is equal to -1. One of the most elegant equations I think you can find anywhere. All right, so enough about that. Using this Euler method tells us that these two functions are really combinations of cosine and sine. In fact, this would be cosine kx plus I sine kx. This would be cosine of kx plus I sine of minus kx, which ends up just being cosine of kx minus I sine of kx. All right, so in other words, when we put the minus I out here, it just changes it to a minus I in here. All right, easy thing to do. All right, so how does this change what we're doing here? Well, it allows us to rewrite the general form of the solution for this equation in this case. So the general solution, we could either write it like this, as we have here, or we could write it as a cosine of kx plus b sine of kx. So in other words, as a sum of sine and cosine type functions. So this is telling us right away this is an oscillatory solution because we know sine and cosine oscillate. So notice a very important difference here. When alpha is greater than 0, we end up getting exponential decay or growth. When alpha is less than 0, this is when we get oscillating functions. So you want to watch out for this because you can tell immediately when you view one of these differential equations like this one up here, if alpha is a positive number, it's going to be an exponential decay or growth. If it's an imaginary number, or I should say a negative number, then it's going to be an oscillating function. All right, so this oscillating function, let's redraw a diagram we had a couple of videos ago of a string that's vibrating between two walls, and it's fixed to each of the walls. And remember, we drew its oscillation something like this, where this represents what it looks like as it's oscillating back and forth across this gap. And we have fixed points here at x equals 0 and x equals L. How do those affect this general solution? So what we want to do now is apply the boundary conditions to narrow down our solutions for this particular problem. Okay, so in this case, our boundary condition is that x at point 0 is 0, and that's also x at point L. Okay, when I plug this one in, when I plug in little x equals 0, I'm going to have a cosine of 0 plus b sine of 0. Well, this is just 0. This is equal to 1, so that's equal to a, but it's equal to 0 according to the boundary condition. So in other words, I can forget the first term. So all I have is the second term here. Okay, what about the other boundary condition? Okay, at x equals L, I'm going to have b sine of k times L, and that's equal to 0. Now I can solve this at 0 two different ways. I could say b is equal to 0, but that will give me, again, what I would call a trivial solution. If my function is just 0 for all time, that's not a very interesting solution. So what is the other possibility? The other possibility is that I set sine of KL equal to 0. And in order to do that, I would note that the sine function is 0. Sine is 0 at pi, 2 pi, 3 pi, 4 pi. It's basically integer multiples of pi, n pi. So in other words, if I set k times L equal to n pi, then I will get sine equal to 0. Okay, or k is equal to n pi over L. Okay, which means that then my general solution for this particular differential equation would be that x of x is equal to b times sine of n pi x over L. All right, so interestingly, the boundary conditions now have given us a much narrowed possibility for the solutions to this differential equation. I'll also note that we would get the same solution basically for the time-dependent part. It would also oscillate, and it'll have a very similar sort of constant, but remember, its constant also is multiplied by v squared. So it's going to be a slightly different constant multiplying time than the constant we have multiplying x. But this gives you an idea of how one can solve, using the separation of variables, a classical wave equation, an ordinary differential equation form, and get oscillatory solutions, and using the boundary conditions specify something much more specific.